It's just the NumFocus slides. So there's some information about what NumFocus and PyData is all about. It's an educational program centered about open code, leading to better science. So this is a list of the various people who are involved with NumFocus and the open code science community. Check them out; they're awesome. I guess we're home to open source projects in the scientific data stack. We're supporting both the users and contributor communities of these tools. If you want to get involved, you can participate in a local meetup. So we're in DC, but in virtual days, you can participate almost anywhere. So just reach out to people. We're an awesome community. You can help organize future meetups. So we're actually looking into maybe reviving PyData Indiana with some friends. We'll keep you posted about that. You can attend the PyData conference. Money from every PyData ticket sale is donating to NumFocus to continue supporting open source projects. And you can volunteer. Every conference needs volunteers. You can donate or work with your company to sponsor or a PyData meetup, conference, or NumFocus. And if you got any questions, you can send them here. I'll share these slides at the end of the event as well. And we want to give you guys a quick reminder about PyData Global, which is happening November 11th through the 15th. So I think today we finally confirmed that we're sponsors. We're going to give a talk once we figure out what's cool enough to show. And we're also going to be hosting a watch party through this meetup group. So we'll figure out how that works, but essentially we will be broadcasting probably through this Zoom channel. And this is a look at all the PyDatas around the world. There's a lot of us. It's really cool. So thanks for being awesome and being part of our community. Okay, now let me introduce Serkan. All right, so Serkan Piantino, and I really hope I'm saying that name correctly.
You got it right.
Awesome. Spent 9 years at Facebook, where he led the build of the newsfeed product, started their New York office, and co-founded the Facebook AI Research Center before launching the Spell machine learning and deep learning platform. He also serves on the board of directors at Carnegie Mellon and Tech NYC. And I'll hand it over to you, Serkan. Everybody who would like some free food, send me a DM in the chat, and I'll send you a code.
Awesome.
All right.
One programming note. Can I get permission to share my screen?
Yeah, of course.
So you can. I think you can add me as a co-host. Somebody mentioned that in the chat. That might be a good solution here.
All right. I think I just allowed everybody to share their screen. So
there we go.
Yeah. Don't abuse it, and we'll be okay.
Okay. And let me make sure my screen is good. Awesome. Well, thank you, everyone. Sincerely, thanks to Hussein for introducing me to your awesome community. Thanks to Paulo for hosting. And yeah, very excited to talk. This is a talk that I've been putting together for a long time. And is really kind of a list of individual blog posts that I think we're going to write, kind of condensed into one. So going to go through a whole bunch of different sort of technical challenges and stuff that we did, give you an introduction to what it really takes to make something like Spell. I'm going to do a live demo, but I also want to leave a whole bunch of time at the end for Q&A. So rest assured that if you have any questions, we're happy to go into any of the stuff that you see here that you want to get more information on. Also, it was explained to me that it's a tradition for the meetup to be kind of simultaneously a happy hour. So I'll be participating. Cheers to everyone in all the different cities. So machine learning infrastructure from 30,000 feet. There's a bit of a story here that ties a lot of the stuff that together, and it does involve an airplane. So first off, just who I am. I already got a great introduction from Paulo, but right now I'm the co-founder and CEO of Spell, and you can find us at Spell.ml. And we started Spell in 2017. Prior to that, I spent 9 years at Facebook, where I did a whole bunch of stuff, most notably building the newsfeed infrastructure and running feed ranking for many years. starting the Facebook office in New York City, which is now, two and change thousand people, and co-founding Facebook AI Research, which is an academic research lab, the first academic research lab within Facebook, and is dedicated to deep learning and artificial intelligence advances. Prior to that, I briefly worked at a place called Bridgewater in finance, and before that, I got a degree from Carnegie Mellon. What is Spell? Well, from a very high level, what we do is we provide this end-to-end platform for machine learning projects. And I'm going to go into a lot of detail on what that means. But basically, we provide this pre-built infrastructure that makes it much easier to get started doing work in machine learning. It makes it faster to get the results you're looking for and make sense of the experiments you're running. It helps keep you organized, and ultimately, it's able to run in infrastructure that's safer than if you're doing this type of work on top of important data on your own. So that's what we are at Spell. And specifically, I think this diagram, let me just shrink this window so I can actually see my screen. Stand by. Whoops. Man, already with the technical details. Okay, whatever. Here, so this diagram kind of shows all the different specific products that we offer, specific things that we power. So training and experimentation, cloud-hosted Jupyter notebooks, a real cool system for running large-scale hyperparameter sweeps, a really elaborate, and actually we'll be announcing a huge upgrade pretty soon, so sneak peek there, to model deployment and monitoring models once they are in production, and then automation and management. And all of that stuff runs on top of a mix of cloud, so any public clouds, AWS, Google Cloud, Azure, et cetera, but also can seamlessly work on top of private machines as well. So a lot of flexibility in terms of deployment and infrastructure. This kind of, going back to 2014, one of my lessons from my time at Facebook AI Research was kind of this equation. Really, AI was this overloaded term. It got used a lot. It was thrown around in a lot of different circles, so it wasn't really very precise. But I think the best way I found to describe what was happening in the world was basically this: that the world is spitting off more data than it ever has before. We have cell phones and sensors, and there's a huge amount of data that we're all creating on a daily basis. Two is that we've made some increases in compute power that allow us to run algorithms that were previously too inefficient to run. Now we can explore them pretty efficiently. And three, we know a little bit more about these models that in the past were actually not, these machine learning models that were honestly not that useful because they were too inefficient, but actually turned out to be really powerful, and we understand a lot about them. And when you have this sort of set of ingredients, what you get is that we can get computers to do things that we couldn't get computers to do in the past. Very simple. So that's how I like to explain AI to people. I think it's a little more clear. And one thing that I like is that, in the media, when my parents or, my friends outside of tech think about AI, it really seems to them like a bunch of scientists in a lab working and sort of inventing something new. And that's very true. That's also, there's a lot of research being done. But I think they miss the importance of the data piece and the very, very important piece, which is just access to huge amounts of compute and how important that is to this type of work. I love this chart from OpenAI. This kind of illustrates the point about computational requirements. All the new stuff in AI, every sort of year that goes by, the new stuff that we're discovering and the new capabilities that we're able to give to computers take more and more compute power. And in this, they kind of divided into these two sort of eras, where in the current era, the computational requirements of cutting edge AI is doubling every 3.5 months. So that is a astronomical pace. This chart is already on a log scale, and you can see that it's increasing really quickly. So compute is clearly the name of the game. And right now, and kind of the state of the world when we decided to start Spell was that large amounts of compute and really the software that it takes to make use of it was really the playground of only a couple big tech companies, Google, Facebook, Amazon, et cetera. And that seemed like a difficult future to head toward, particularly for something like AI that's done in the open. It's done as academic research. It's something that anybody can engage with, but unless you really could amass and unless you had the tools and the access to big, powerful GPUs, you weren't really going to be able to participate. And that was bad, we thought. So this is one of our main reasons for starting Spell. Just to put some numbers behind it, this in 2014, we open sourced the design for this machine, which was our first GPU design at Facebook. We called it Big Sur, and just for scale, Deep Blue, which was a supercomputer that was the first to beat humans at chess, that had 96 gigaflops. One of our commodity web servers at Facebook was 800 gigaflops. This machine was 56,000 gigaflops, so quite a bit more powerful, and now state of the art. One NVIDIA A100 DGX1, which just came out, is 156,000 gigaflops. So many, many orders of magnitude in terms of compute capacity that we're routinely, using and throwing at one problem. So a bit of a story. So when I left Facebook, I became, I was already kind of addicted to having access to these sort of like giant how-powered machines and training neural nets and doing all types of things. So I started building them myself. This is my first one. It's got a whole bunch of Titan X's in it, and you can see the optimized cooling, some impressive cable management. And I had this running in my living room, producing copious amounts of heat and noise. My girlfriend was not super excited about my new hobby, but I would use it to train neural nets and to sort of continue some of the research that I had done at Facebook. And it turned into a little bit of an obsession. This is, probably $30,000 worth of Titan X's sitting in my living room.
Serkan, tell us why you didn't choose the liquid cooling in that setup.
Liquid cooling is messy. It seemed ineffective. I didn't have that much experience with it. And one thing that I really wanted to be able to do is I built one machine, but I really wanted something where I could just assemble these things at rapid speed. And liquid cooling's it's a bit of a beast. So instead I bought a bunch of commodity cases, and this is, I think something like 30, or this is probably, I think more like 20, but I started buying a lot of GPUs and spending a lot of money on this. And again, the noise and heat coming out of my living room became pretty powerful incentive to get out of the house, I guess. And really one thing that I was doing is managing all these machines myself. So, I had them all in my local network. I'm SSHing into each one, copying code onto it, running experiments, trying to treat this like a compute cluster was super difficult. And I couldn't remember which machine I had used. And so I would go onto that machine and I would try to figure out in what directory I had left the model that I had trained, and then copy that somewhere else so I could run it on some imagery. I mean, it was really, really kind of a nightmare. I spent very little of my time actually getting interesting results with deep learning, and a lot of my time, doing 2005 era sysop management type things. And the thing that occurred to me is is this what anybody has to do if they want to get started? Is this is this how you do things in at the time, 2016? Is this what it takes to get started in AI? That can't be a good thing. That is clearly a barrier, sitting down and assembling hardware, optimizing PCI lanes. This is not what people signed up for, especially people in a community like yours. You're used to using Python. You're used to using cloud offerings. There's just so much better tooling that makes this not really a problem we have to solve. Something's got to give here. And, so I think one of the key insights that we had early on was that everything that I need to specify to run an experiment is actually pretty lightweight. So, what I really want to say is if I run this code at this commit hash, in a Git repository somewhere, if I run it in this software environment, so these packages are installed, some sort of container, if I run it with this data specifically in this, mounted in this location, what am I going to get? That's really the question. And the fact that I can specify all these things in a very lightweight way really led me to think we could build an API where I specify exactly what I want my experiment to be, and another piece of software can figure out what hardware I need to run it on, how to orchestrate that hardware, can keep it up and running, and eventually can organize and return back to me the results of running that experiment. And so that's kind of the vision for Spell. And really the story here is about going from that idea to the first version of Spell, which we launched in 2018, which really had three pieces. We did build exactly that REST API. I thought about including the API spec in the presentation, but it has grown quite a bit since then. So probably a bit outside of the scope here, but it is that REST API. It's also a command line tool where we can accumulate a lot of the ingredients about what experiment you want to run just by you typing spell run in front of something you would have automatically run locally. And then we built this really slick web dashboard where you can see kind of like the PS command on your in Unix. You can see all the things that you have running. You can keep track of them. We give you kind of a cool experiment report. We automatically collect metrics and stuff like that. So a lot of product around this, like a really full-featured, delightful way, a lot better than slapping GPUs in your living room and trying to go at your own. And with that said, I figured the best way to talk about this would just to be a live demo. So I'm gonna do a couple spell runs here, and we'll see what that looks like. So first, let me pull up our web console, and we will. Excellent. And just to, it's okay. Just for the purposes of this demo, I'm going to pull off, I'm going to do this live. Let's get a copy of Keras from GitHub. I'm going to pull some code off of GitHub. Specifically, I'm going to clone Keras directly off of GitHub for a couple of reasons. One, I want to prove to you that I didn't do anything fancy here. This isn't some like canned demo. I hate it when people give canned demos. And two, Keras comes with a whole bunch of really neat examples that are easy for me to use. So first I'm going to try to run one of these locally. If you've tried this, I don't necessarily recommend installing TensorFlow and Keras on your local machine and trying to do deep learning on a MacBook Pro. You can, but it's not a particularly nice experience. But just to illustrate, I'm going to show what happens if I try to run a deep learning model. In this case, CFAR10, which is some thumbnail-sized images, and we're going to try to identify objects within them. So relatively sort of like a hello world-ish type example, but we can see here on a MacBook, this is going to run through the data 100 full times, and each one is going to take 2 minutes and change. We're already looking at a few hours for this model to run, and if I close my laptop or I try to do anything else, it's going to interrupt this process. So not a great workflow. Instead, here I'm going to type spell run in front of this command. And I get a whole bunch of options on the command line. There's like a lot of different ways to configure how this is run. I'm just going to use one and request a machine. I'm going to request a T4, which is a machine with a GPU, which I know will very much accelerate this, and let that run. So what Spell is going to do is it's going to sync exactly the copy of the code that I'm working on using the commit hash, and any unsynced changes will also get synchronized. We're going to find a machine of that type in one of the clouds. We are going to assemble a container with the code and any requirements installed. We're going to start the process, and then we're going to stream the logs back to me just as they would have appeared if I had run this locally. And what's nice that you might notice is that it takes like 5 or 6 seconds. You had 5 or 6 seconds of overhead. Otherwise, it kind of feels like I just ran this command. But this is now running in the cloud on a GPU somewhere. And as you can tell, it's running a lot faster. So I'm going to Control C out of that. Go back to my web console here. I can see I have this running job. I can see all the details here, the command that I ran, the commit hash, the machine type, etc. If I want to, I can click this button and rerun an exact copy of it because we have all those ingredients that we need to reproduce it. And I get metrics about CPU utilization, memory, network. We can see the GPU is doing some work. And we also have some magic stuff that we do. So here we're automatically hooking into the keras fit function and automatically pulling out into our metric system things like loss and accuracy, etc. If this process ends up writing anything to the file system, I'll see that here, and I can access those live as well. And then, of course, down here I have these live logs where I can take a look at it. So yeah, sort of, we started with this big idea of just being able to send stuff up and have an API for specifying and some software to handle running the experiments that we wanted to run. And here it is. And I'm going to talk about why, even though this is a simple experience, it's pretty easy to explain to anybody who's technical, anybody who uses a command line. There's a lot of machinery that goes into this and some pretty interesting technical problems to solve. So that is the live demo. All right, moving on a little bit. The first problem that we run into is just the run orchestration itself. So if you think about all the different states that a machine can go into, all the different things that can go wrong, all of the different steps that we're actually using to orchestrate and run your experiment, a lot can happen, particularly when an experiment is running for hours, in this case, or sometimes days or weeks. And one thing that we decided early on is if we're building an API, we can never forget about something that you've given us. We either need to see it through to completion, retry a couple times, or we need to tell you that it's failed. So what that immediately means is we can't rely on some process that's running on the machine. We need to have our own record of what state the machine is. We need to keep tabs on it and work it through this state diagram. And also another subtle sort of challenge is that if you're using different hardware, you often need to build the container on the exact hardware that you're going to later use to run it. This is particularly true for GPUs. The versions of the drivers, the versions of packages that you'll get from pip can be very different, and they can install very differently based on the hardware that's available. So we also need to build containers on the same machine that they're going to be run in. And this orchestrator, I didn't show it, but we have a really powerful hyperparameter optimizer where people do hundreds or thousands of runs in parallel. And that puts a lot of burden on our orchestrator. So everything that we do here, everything that we do to keep track of runs and make sure we work them through this state diagram needs to be distributed and needs to work on multiple instances. And finally, the one contract we make is that even if something goes wrong in this process, we're still going to have access to the outputs from your experiment. We're still going to save any files that you wrote. And that becomes really important later because a lot of our customers are able to use spot instances in a safe way and still get results and save about 75% of their costs if they are using cloud GPUs right off the bat, just because they're using spot instances and can still get their experiment outputs. And actually, why not? I'll call out Ben, who's in the audience today, recently built an auto restart feature. So you can use spot instances. Not only will we save the results, even if your instance is interrupted and goes away, but we'll also restart it and keep it running so you can finish off things all on top of spot instances. One other thing I'll point out is that this state diagram, which is how we work through the different states within Spell, looks a lot like if you pull up a process diagram, a process state diagram from Unix or Linux, it looks very similar. And that's kind of been a theme for a lot of the stuff that we've built. We're building these sort of same primitives when we talk about file systems and how we handle data. We're building these same primitives on top of the distributed cloud or private machines. So a lot of what we're doing does resemble the work that goes into building an operating system. So our run orchestrator, I would go into the technical details of how we solve all these problems. Unfortunately, like the details of locking and state and multi-threaded Go libraries are like pretty deep, and I think probably outside the scope of this talk. But I did talk a couple features that built into it. So going back to my story, I showed it to one of my colleagues, Sumit, and Sumit, you may know because he was actually the creator of PyTorch, which is now, I believe, the most popular deep learning framework out there and has taken over from TensorFlow. But the first thing he said to me when I showed him an early beta of Spell is, if this takes more than 10 seconds to start, I'm never going to use it, which was a little crushing at the time, but was very good feedback. And it led us to a feature that I don't think anybody else has built, something we call instance caching. So as you can see when I ran, we're only talking about 5 or 6 seconds of overhead when you run something with Spell. And we really want that. We want Spell run to feel just as seamless as if you were running the command locally. But it's important practically too, because a lot of times you run a script or you have a bug in your code, you have a typo, the thing's just going to fail and exit immediately. And if you have to wait to get that feedback, it's going to slow you down a huge amount. So that sort of interactive nature of running things is really important. But if you spin up a new instance in the cloud, that can take anywhere from 5 minutes for smaller instances to 15 minutes to way longer than that, depending on what you're using. So how do we get this? How do we not just have hardware that's up and ready to run immediately, but how do we do that in a way where it doesn't cost us a huge amount of money because we have instances sort of just like piling up doing nothing. So I'm really proud of how we solved this problem. We have this like really flexible thing called a cluster manager. And what this does is it will automatically keep a lot of cheaper instances around and idle and ready. And so that's things like lightweight CPUs. If you just want to run, a lot of people run wget on Spell to get some data in, or just anything that's sort of interactive, you can run on a CPU really easily. For expensive instances, we do fire them up on demand, but we keep them around for an idle timeout. And what that allows is if you're doing, lots of subsequent work, you're going to end up getting that interactive experience on the same type of instance, or especially when you have a lot of people sharing a cluster, the probability is, if you get in work in the morning, somebody else has already used one of those instances and we have one waiting around. So the TTL really helps. It creates that sort of like instantaneous vibe, but it also will shut down instances automatically for you so you don't end up wasting money. And our cluster manager does exactly that. It manages these pools of idle instances. It will also do things like in the background, recycle what AMI we're using, update drivers, kind of like always keeps track of what machines are in what state and what state they need to be in, and handle all those things for you behind the scenes. And this has a huge number of benefits. Just those two pieces of software together give us a lot. So because our cluster manager is just thinking about instances, and because the clouds have similar APIs, we immediately, from day one, have been multi-cloud. So we can seamlessly kind of run your instance on AWS. If it becomes cheaper on the spot market to run it on GCP, we can run it there. We're launching support for Azure pretty soon. And recently we also deployed a really easy package that you can put onto your own private GPU machine, or any machine really, and use it alongside your cloud. So by default, it'll go to your GPU, but if you end up needing a little bit extra capacity, we'll burst that into the cloud. We also anything that we do here for our community product, you can just sign up for you can sign up for an account and we'll run that on our own clusters. But we also built the ability to run these things within customers' own Amazon AWS accounts and their own VPCs. So that turns out to be really important if you're working with startups or anybody that's handling sensitive data. They're probably not going to let it leave their infrastructure. So we can kind of terraform into somebody else's account, even within their own cloud. And we have some other things that are pretty cool. We'll interactively monitor the instance, and if we detect that you're about to run out of disk space, we'll resize the disk underneath it on the fly and sort of save you from failing your job. And one other tip is that if you're running a startup, probably similar to us, you get a lot of cloud credits from the different clouds. It's very competitive. They all want to compete for your business. So you might get $100,000 of free credits to use on AWS and $100,000 on Google Cloud and $100,000 on Azure. So we have this blog post coming up that kind of goes into more detail on this, but between the, roughly $100,000 you can get from each of the clouds as a startup, and between using spot instances and using Spell to automatically route between them, you can get something like $1 million and change in completely free GPU compute and training without spending any money. So so pretty good idea if you're doing an AI startup, and we'll have details of that in a blog post pretty soon. So so that's kind of run orchestration at a high level. The next sort of ingredient is building environments. So containers are kind of a great solution to making sure that multiple people can run code in different software environments. They can specify those environments. We can have control without having to build virtual machines and deal with Python versioning hell, etc. So our original idea was that one of the things that you would submit with every experiment is this sort of is your own Docker file, and that gives you a lot of control. We figured people would be really comfortable with that. That'd be the easiest way to go forward. And this actually doesn't work that well for a number of reasons. First of all, the people that we're trying to provide Spell to don't really want to spend their time writing Docker files. And if you have to write one before running anything on Spell, it really is a very sort of cumbersome thing and a barrier to entry and just getting started. Second, one of the most frustrating things with getting, especially if you pull down somebody else's code from GitHub, getting it to work involves things like getting the right Python version installed, installing CUDA libraries, making sure the right frameworks play with those libraries, dealing with, pip version hell, probably installing virtual env a couple of times. These are all the not fun things in doing machine learning and data science. And we're supposed to be doing these things for people. So if we just ask them for a Docker file every time, we're not really making their lives easier. Third, we figured out that basically everybody was using the same core set of mainstream frameworks and libraries. Everybody's using pandas, everybody's using scikit, everybody wants access to NumPy, et cetera. So mostly we were finding the exact same things in packages, and we knew that we could meet 90% of what people need with just one set of things. And then Docker files also are, they can easily be mangled. So it's really tempting to put all types of preparatory work or anything that you don't feel like doing in the Docker file itself. And while that's really, that can be sort of convenient, it also means that we can no longer guarantee that we can reproduce the experiment. If the build step did all types of things that are not reproducible, that sort of breaks our vision of an experiment API and keeping reproducible results. And then finally, we had all these visions for magical things that we want to do, and they require access to the environment on our side. So a couple things like we can turn any of your runs into a Jupyter kernel and then give you a Jupyter interface that's running against that hardware in that environment, et cetera. Or one of the things I showed in the demo is automatically building some hooks into major frameworks. So we're automatically collecting metrics from things like TensorBoard or, Keras, et cetera. So, oh my God, there's a slide missing. So one of the things that, my apologies. So the way we end up handling this on Spell is we prepare and we go to a lot of work to make sure that we have exact versions of containers that with the exact frameworks that work across all different types of hardware pre-baked for you. But then we give the user control over any pipped packages, any apt, you can support, you can submit a conda file. We give you all these tools on top of that for adding things to your environment and specifying what you need to run your experiment. And then for, sort of power users or times when the container that you want to run is very custom, we do support, you can either give us a Docker file if you prefer, or you can give us a tag on Docker Hub and we will use that container instead of our own for running your experiment. Although you don't get some of these magical features that we're very proud of. So that's environment building, just some of the things that we learned about what the product needs to be and how we can get to the most usable version of Spell from what we thought we were going to build. And then finally, just some stuff about data management. So a lot of times, if you think about my cluster, you're dealing with huge amounts of data. The sort of like first thing that you start off doing when you're managing these things is just copying your data directly onto either the private machine that you're using or the instance that you're using in the cloud. And this has a number of limitations. The first being that you're limited to just how much storage is available on that local machine. And you can routinely have data sets that cross into the tens of terabytes. There's some public data sets for self-driving models that are well beyond that. So that becomes limiting pretty quickly. It also just takes forever. I don't know if you've ever tried to copy 300 gigs of ImageNet onto a machine in the cloud, but you're looking at hours and days before you can even start running your experiment. And then the final thing is that once you have data sets spread across all these different instances, you're using the local disk, you're also going to have results spread across different drives, different instances. And so nobody I know that does deep learning doesn't have to build some sort of, Bash script or Python script for like automating this process, keeping track of what they're doing. And usually those things break in pretty painful ways. One thing you might be tempted to do, and actually was our solution at Fair, is to build a sort of private cluster and use your own sort of network attached storage to handle data loading. And this can work sort of ergonomically. But if you really think about all the different demands that we're putting onto this network storage system, what's going to happen is it's going to break down pretty quickly. First of all, we have to support fast random reads into a data set. So your machines are going to be loading huge data sets, sometimes in completely random order, sometimes pulling one image out of a pool of 1 million of them and literally shuffling randomly between this giant data set. That really thrashes reads, and it puts already this huge load on this network attached file system. Simultaneously to that, you have logs and metrics and things that you're probably looking at tailing or you want to see in real time. So the system also has to optimize for these low latency writes coming in from experiment machines and going out to people who care about them. You also, once in a while, are going to do these huge, large batch writes. So if you do, if you serialize a model and that has 1 billion parameters, you're looking at a couple gigs every time you write a checkpoint that has to go back and be cataloged on this machine as quickly as possible. You need high consistency. So a lot of times if you're synchronizing code or files between multiple people, you're going to want to make sure that nobody's overwriting each other, and that consistency guarantee, particularly if using any type of distributed storage system, is going to slow everything down quite a bit. And basically what we found at Facebook was there is no system that can do all these things extraordinarily well. This is a incredibly difficult workload for really any network attached system to handle. So one thing that we see a lot of people doing is using just basic cloud storage like S3, and that's fine. That actually has a lot of benefits. You do end up being bandwidth limited. So if you're limited in the amount of data that you can pull down on your machines by the size of the network pipe you can get to them, particularly if you're using private machines, getting a direct connect to AWS so you can get better bandwidth to S3 and actually feed your GPUs is actually a really expensive proposition. But the bigger problem is S3 is a really bad solution for anything streaming. So if you want a chart of any of your experiments, if you want to look at logs in real time, there really isn't a way of using S3 as this sort of streaming system where you can look in real time at what's going on. And even if it could do that, there's no sort of like automatic organization that you're going to get with Object Store for where your data is. And there's no link from this log file was created to any of the data that's living, any of the data set, any of the code that linked it. It really still becomes a pain to manage. So in order to just to get our V1 out the door, we built this much more sophisticated system that we call Spell.fs. And what we present to the user is just one single file system that has all your data, all the models that you've trained, all the outputs for all of your different runs in one place. And we really like that it uses the same sort of Unixy folder structure. You can browse it using ls and cp and cd. It really does present to you as one file system that you share across your whole team. But it actually runs a custom Fuse-based file system on each of our instances that is optimizing between streaming from the cloud and locally using local storage on larger data sets. So what that allows us to do is when you do a spell run, you're going to get that data that you want mounted immediately. You can start doing operations on it. The software is going to immediately start streaming it over the network. But if you're doing something that's very I/O intensive, instead of constantly streaming data over the network, we have a whole bunch of code that is going to optimize how to use local disk. And ideally, if you're reading the same data over and over, you're going to see that I/O throughput get back to about the performance of what would happen if you copied data onto the local disk. We also use a totally different dedicated system for anything that we want to appear in real time. And the system we use is Apache Kafka. It's really good. It's really scalable. It meets our needs quite well. And that's what allows us to do things like stream logs with very low latency. It allows us to show those real-time metrics charts. And it really gives us this second path for data with a different sort of access pattern alongside using cloud storage or local storage and our sort of custom stuff that runs on instances. And what's nice about putting these things together is instead of looking for your data in some file system, a different interface, literally right next to the command that you ran, you have a record of what outputs it created. And we're able to automatically catalog everything, put it in the same system. So not only can you keep track of what experiments created what results, but you can also use the output of one experiment if you trained a model or something like that in a subsequent experiment without ever having to copy it to another location, et cetera. So a lot of work here in data management. And again, this is a blog post that we have in the works, but going into all the nitty sort of benchmarking details and how we build Fuse file systems and get them to run across all these different instances. Sort of a lot of cool technical work there that we're going to go into next. And so I wanted to give a little bit of a briefing on where we're at today, where all this has kind of landed us. This same chart, again, we do everything, from the training and experiment tracking stuff that I showed earlier today and as part of Spell V1. We do have cloud notebooks. We have a really sophisticated automated hyperparameter optimizer for running these experiments in an automatic way and at large scale. We have a huge model deployment infrastructure that comes with free monitoring. So you can easily, take something, a model that you trained in our system and deploy it into Kubernetes and have it auto scale and hit it as a REST API, you know, a couple minutes later. And then finally, all of the things that we do are exposed via our CLI and the web, but we also expose via a Python API. And we have a workflow system for doing automatic sort of meta learning and doing, you know, more complicated scripting on top of all of these elements for workflow automation on top of Spell. So, you know, just a little, this is our infrastructure today. This is between running machines in different clouds and on private machines and all the different pieces that go into Spell today. So we've come a long way from V1. And then, you know, final obligatory plug, we're hiring. If you're excited about the idea of not just working on the infrastructure behind the next generation of how machine learning can be more efficient and more accessible, but also all the cool problems that we have to solve around ergonomics, some of the stuff I talked about today, and more on the product side, you know, defining the future here, then come look us up. Come to Spell.ml and visit our jobs page and read about our culture, and hopefully come join the team. That's it. Again, thank you, Hussein, and the rest of the PyData team for letting me give this talk. And I think I'm gonna open up to some questions.
Yeah, thank you so much. This was amazing talk. Really, really appreciate it. What kind of questions do we have?
I see some things in the chat. Oh, mostly about food.
Which is an important part.
Yeah.
So,
I mean,
okay, backing up a little bit,
yeah.
Serkan, so you got a 1600 watt PSU. Like,
Yeah.
what kind of electrical work did you have to do in your house to like run it?
So this is in my apartment in New York City. I have no idea. I never blew a fuse somehow, but I'm sort of surprised by that. But yeah, the power requirements are also, I didn't pay attention to the electric bill, but I'm sure it was a lot higher.
I just did a build, and I had a socket with my PSU that I texted to Eric Dill, and I was like, "Hey, what the fuck is this?" And it like, yeah, it was basically a dryer socket.
Oh, really? You had a 220 power supply?
Yep. Which we were not using anymore, but yes.
One of the things we did early on, because we had, you know, so the first version of Spell predates actually being able to get any kind of reasonable GPU on the cloud. So we ran on top of our own cluster. We literally had it in a closet. We were touring data center space. Like we were gonna build all this stuff ourselves. And when our machines were idle and we didn't have a job running on them, we would actually mine Ethereum. That was like one of our second revenue streams for the business. But
2017, that's really good business, man.
Well, you know, it wasn't as lucrative as you would have thought. But and also we kind of felt bad because it's, you know, one nice thing about, okay, so another story is we got approached. I went to visit, actually I came to DC in your neck of the woods to visit some students at the University of Maryland who had built this like peer-to-peer sort of like leasing business. A lot of them had built GPU machines and were mining Ethereum at the time. That was like a very profitable thing to do. But they would lease them to each other and charge them lower than cloud costs to use them, to rent them out to do deep learning work. And you would actually get paid in Ethereum. It was like a really cool system. So we talked about doing this like peer-to-peer thing and, you know, getting access to all these different GPUs, but it presented too many security risks for customers that want to use it for real stuff on real data. So we didn't end up pursuing it. I think those companies still exist though.
That makes sense. Yeah.
Hey, Serkan, I've got a question for you on data. How far kind of up the data pipeline are you going? I mean, kind of the one demo, you know, was obviously assuming like, you know, perfectly clean data.
Yeah.
I mean, how do you handle kind of that like horrible part of the whole data science lifecycle?
And it is horrible. So I would say there's two kind of regimes. You're right that we are assuming perfectly clean data. There's two kind of regimes. So for customers that are doing deep learning, generally, I think this like task of data cleaning, which is still sort of like top of mind, actually transforms into more of a data labeling challenge. So a lot of those, and so we have some customers, we partner with Scale on some customers that we work with on the autonomous side, and there's some other labeling providers and places you can get labels. That ends up taking the place of like the usual data cleaning pipelines and stuff like that. Two is that for people who are doing more traditional machine learning, we see most often the way that they're doing data cleaning is within Jupyter notebooks. And so the system where, you know, you can fire up a notebook, you can do some stuff in there, and then whatever files you had written to the file system, whatever you had access to there is immediately accessible to scripts. That sort of helps that process quite a bit, makes it a little bit more seamless. But I would say, to totally answer your question, is like, we haven't found a magic technique or algorithm for data cleaning. I think I have seen some interesting work in sort of like cross-validating data and detecting anomalies, doing things like, there's one of our advisors actually started a company where they will train a small machine learning model on every segment of your data, and they will use, if the machine learning model can differentiate between this week and last week as a signal to anomalies and changes in your data. Very interesting stuff. But unfortunately, when data is unclean, it is humans who have to do the work of making it cleaner.
We've got a question in the chat. So somebody asked, we are an early data analytics startup. What is the right infrastructure we need to build? Do any of the clouds come close?
Yes and no. I think like these days, if I were starting a startup that wasn't, if I were doing a very deep learning heavy startup, which a lot of people are, cost would be one of the first things I think about. There's a great blog post by some people whose names I forget it, Andreessen Horowitz, that goes into some of the meta learnings they have about how cost ends up eating some of the margins you'd expect in deep learning businesses. But for data analytics, I would default to using the cloud. I would use some sort of organized cloud Jupyter solution to begin with. The clouds often have these things baked in. One subtle thing is that, for instance, something like SageMaker, if you use Amazon SageMaker is 40% more expensive. They use like special instances that they tag, and they end up charging you 40% more for. And generally those products aren't very good. Like the analogy I use for those is like these clouds, the teams that build them, they're infrastructure teams. They build these like, you know, they're used to building plumbing and heating and, you know, HVAC systems. It's like sometimes when I use some of their ML products, it kind of feels like I'm going into the basement and like opening the fuse box, and that's where I'm sitting and trying to do some of my my work. They're just not really like product oriented ergonomic teams. So, you know, I would check out stuff. Definitely we have things that are going to make that a lot easier. You know, and we're a lot more affordable than the 40% markup you get in the clouds, but also check out stuff open source and try to build your practice around reproducibility, like treating this, you know, treating the work that you're doing with the appropriate level of management and respect, like the way you would treat, you know, you're not just going to like SCP some code onto a server. You're probably going to use Git. You're getting into these practices earlier is only going to make your life easier in the future. And particularly when you go to hire people, you know, if you don't have like any sort of organization around some of these processes, if, you know, you're like, well, how do we reproduce that analysis? How do we do this again? If like your answer to that is just pointing to somebody in the room, that will break. And I think, you know, investing in the tools early on will definitely pay off in the long term and probably in the short and medium as well.
We got another question from the chat. Somebody would like to, you know, get the nutshell version on the differences between machine learning and deep learning.
Yeah, great question, because I don't think I ever really defined that. So I guess the kind of long version is that machine learning is the field. Machine learning is like the idea that, I mean, the way I put it to people is that you, instead of telling a computer how to do things by programming it and giving it specific instructions, you say, well, I have a whole bunch of examples about what I want you to do. How about you just like take a look at those examples and figure it out on your own? And that's kind of the general purpose, the general idea of machine learning in a super layman's terms. But deep learning is kind of a subfield in that, and it's really a rebranding of neural networks, which were a very sort of, they're inspired by how the brain works, or at least are like sort of modeled in a little bit of a way about how the brain works. And very early on, by the 60s, there were theorems proven about how even just with stacking neural net 3 layers deep, you can optimize any function and you can approximate any function. Have obviously been powerful for a very long time, but nobody could do anything practical with them. They were kind of a backwater. So once GPUs came along, and once people started using these things with enough compute power to make them useful, they became very in vogue and kind of have now, in terms of research and state of the art, neural nets in NLP and in computer vision, in autonomous driving. You know, neural nets are kind of the machine learning application, the thing that started this recent wave in AI. So that, because neural nets were really, honestly, like kind of something you couldn't study and be taken seriously in academia, they had to be rebranded as deep learning. And that's sort of the buzzword. But basically, to summarize, deep learning is a subfield of machine learning that really deals with neural networks, specifically that one technique.
How does sort of a continuation of that, like how does transfer learning play into deep learning, but also like how does it like to play into organizations who are, you know, trying to adopt these things?
Yeah, I mean, it's huge because a lot of times you talk to an organization with a problem that could be solved by deep learning, but they don't have enough data. You know, you don't have a million examples. You know, just as like a basic example, there was one of my old friends that still works at Facebook was trying to hook up a webcam and train a neural net to detect when the UPS guy came so he could get a push notification and stop people from stealing his packages. This is a San Francisco thing, unfortunately. So, but he doesn't have, you know, 10 million labeled examples of UPS people outside his front door in every weather condition, et cetera. And so that's where transfer learning comes in. What you find is that for a lot of these neural networks, for a lot of these things, what they learn is maybe 90% like general purpose, what humans look like, and, you know, how to detect edges and objects within images, for instance, in computer vision. And a small percentage of it is like very specific to the task. So you take a pre-trained model that's trained on a whole general corpus and kind of knows how to do some version of vision and do transfer learning. So that's what transfer learning is. I would say this, we're starting to see it more and more. That's one of the biggest trends. Early on, it was like hard to find examples in the wild of people successfully using transfer learning. And there was this like era where some of the results were really kind of ugly, where you take some like general vision network and you modify the task like only slightly, and it ends up performing really poorly. And so there was this sense that we'd overstated, you know, how good these things are. But now you see transfer learning all over the place. It's probably where most people start, and you see it actually working. So basically, if you have a deep learning appropriate problem but not enough data, all is not lost. You can definitely still try.
So you can basically, in like, you know, sort of the AI way, you can take some knowledge and apply it and like fine tune it on a just similar problem set.
Exactly. And so that might mean, you know, if you, by the way, Fast AI, which is an online sort of deep learning course, is like really, really good at not only explaining this concept, and you work through that on a few examples where instead of training the entire neural network from scratch, you download a pre-trained neural network and then retrain some of the top layers that are doing, you know, some of the coarse decision making. But also they have frameworks for doing this. That's exactly right. You train, you find some widely available data, and that you have in huge amounts, and you train a giant neural net on it, or you download a model that's already been trained on that exact corpus, and then you take your smaller amount of data and you run it through and sort of fine tune it towards, so it's making decisions based on that, but still benefiting from all the prior data it learned from.
That'd be one way from like going from like 1 million labeled examples to like 10,000 examples.
Exactly. But, you know, it's really, I think one thing that we focus on a lot, we have to explain, is that you don't know. You know, there's no, like when people ask me how much data will I need to fine tune for this task, there's really no way to tell. And that, I think what you said highlights that these, you know, machine learning projects are different when it comes to resourcing. They're different in workflow. They have more iteration cycles. They tend to be more circular than like if you work on a usual software engineering project, you kind of march through it and get to completion. And they're riskier. They're more experimental. And I think what we find, a lot of our customers are in the enterprise space. They're larger organizations. You know, in 2016, 2017, they were investing in more machine learning practitioners. They were getting their data in order. Some of them were doing deep learning. They were taking machine learning, traditional stuff more seriously. And between 2018 and 2019, what they found is like, we don't know how to do this. We don't have the tools in place. We're not used to how experimental this is. We're not used to how, we don't have all those things. And that is why, you know, now when we talk about Spell, we talk about MLOps, which is the name for the industry that was birthed from the frustration, basically, of the industrial world trying to figure out how to do this stuff, you know, for real. So, yeah, free to decide.
So I have a workflow question for you.
Sure.
So that you just showed us in the demo of the workflow where I'm able to run something on my local machine.
Yep.
In like enterprise, in my experience, that is never the case. Like you never run anything on your laptop. You're always logging into a server, SSH doing it, you know, however your mechanism might be.
Yep.
So that workflow, like how is it different from the CLI-driven workflow, or is it the same? Also adding the data locality challenge, where my personal or like my enterprise laptop may not have the access to the proper resources.
Yeah, great question. And this comes up all the time. So one is that we try to move people away. Well, I guess three things I'll say. One is that we support, you know, every cloud. We support private machines. So usually we go into an organization and maybe they have their own provisioning system. Maybe they're already using Kubernetes or containers. But generally we can make a spell run happen on pretty much any setup. I think one thing we say is like anything that looks like Linux can run on SSH and can run Docker is like a potential target for a spell run. It's like very, very flexible in that way. And that's what we found. I mean, a lot of companies just getting into this space are sort of shocked at how many different configurations. If you're working internally on a company's data, you kind of have to go where they feel comfortable their data going. And that is a wild, wild west. So you have to build for sort of lots of different scenarios. Two is we get people out of the like, I'm going to log into a remote machine and do my work on it. We try to get people out of that because it doesn't end up being reproducible. It's a good way to interactively do your work, but ultimately, you know, all of us are writing Python scripts and we're routinely asking this question, what happens when I run this on this data? That is, if you do that in a structured way, if you do that with something like Spell, not only does it work the first time and it doesn't take you any longer, and maybe it saves you from having to SSH and figure out where machines are and stuff like that, but also you have a record of what you ran. You can reproduce it, you can send it to somebody else, you can learn from it over time. Whereas if you're just like, you know, using machines, you know, there's nothing wrong with using machines interactively, but if you're doing something that's an experiment, you should tell the support infrastructure that you'd like to run an experiment. And then the final thing is about data. I mean, part of the reason we built, and we put a lot of effort into building a fuse file system that runs on every instance, is so that anything that might look like a file, we can mount remotely and also manage the caching layer on top of. So, being able to use something immediately, being able to just have instant access to it over the network, but then also having like full control over how that's cached and what the performance characteristics are, really helps. So we go into an organization, if they have, specific file server, if they're using Hadoop, like all of those things are really just like file-ish targets for us, and our file system can handle. Or, sometimes, as is true in enterprise software, we say it can handle it because it will be able to by the time we're able to sign the contract with the customer anyway. Anything that looks like a file, we either support now or will support relatively short order.
I've got another question from the chat. What is the biggest cost saving that Spell offers compared to custom builds or SaaS ML platforms? At what point in a project should teams evaluate Spell? Coming to Spell, I guess.
Yeah, I mean, as I said earlier, I think like the best practices that we've put in, and just like treating an experiment like an experiment, giving people one interface where all of your work goes, I think those are valuable from day one. Another sort of subtle thing is I use Spell, honestly, more often when I don't need a GPU than when I do, because I don't like using virtual env. I don't like, designing, I don't like managing what Python versions, and I often am running something that probably will run for a couple minutes. There's no reason for me not to type spell run, add a couple pip packages, and have that run somewhere on the cloud than running things on my local machine. Running things on my local machine these days feels a little weird. So I would say it's useful in the earliest stages. It's just like kind of one piece of things, and it's also not particularly expensive. So you're welcome to give it a try. It's in terms of cloud savings and cost, I would say a couple things. One is there are not, any SaaS product out there is not going to alleviate the cost from you. Almost all of them, like a Databricks, for instance, people use Databricks. What may not be clear is that Databricks charges you, but you still are using your own AWS account and you're still getting billed for all those instances. So ultimately somebody's providing a piece of hardware. And I think what we try to provide is flexibility so that we could move to different pieces of hardware if you have credits, or you find something that's cheaper or something's more appropriate. You want to use TPUs on Google, but you have credits on AWS, that type of setup. Spot instances and preemptible instances, which is what they're called on GCP, are a quarter of the price. So the fact that you have software that's automatically managing them, finding them, and allows you to use them with more of a net under you than you normally would have, that is a huge driver of cost savings. And then the final thing I would say is beware. I mean, it's not the end of the world, but beware of the ML tooling that's built into the clouds. It's not particularly good. It's designed to lock you into that cloud, and it uses all of the other infrastructure that the cloud has as awkward solutions to some common problems in ML. And I think it's sort of deceptive that without really telling you, it will take the same instance, call it a different thing, and charge you a 40% markup. It's not obvious, but it's exactly how it works. So I would say, some tips on, hopefully that made sense.
We've talked a lot about training. I'd like to hear more about the deployment. That was kind of a block that you checked pretty quickly there. But, obviously managing a production infrastructure is its own full-time beast. So are you producing a container that then gets kind of, put in the right place in an infrastructure, or how does that deployment work?
That is, okay, so I'll tell you how we used to do it and why that was a terrible idea. And then I'll kind of go into how it works currently. So our first, we saw a lot of people using TensorFlow. This is before PyTorch really came out, or scikit-learn. Those were kind of the two major worlds that we saw in terms of ML models. And so the first version of our infrastructure, you would literally just click on the model if it was an output, and you would say deploy as API, and we would gobble it up. We had pre-built containers as part of our init process. If we're deploying, if we're using your AWS account, we had already created a little Kubernetes cluster. And so we would automatically register it. We'd turn on auto scaling. We'd use our serving containers, and boom, like a second later, you would get an API that is serving your model. This is a bad idea. It sounds nice, but this is a bad idea for two reasons. One is that it's rare that the model itself is the API that you want. It's much more often that you need to pre-process the inputs. You need to do something. There's just something a little bit different that you want to expose in the API than what the model itself is. So one is that almost everybody needed some sort of like way to register a handler and write their own code to pre-process or post-process inputs. A. B is that if you talk to any company of any reasonable size, they're going to have stuff they need to put in a container. They're going to want their security infrastructure. They're going to want all these different things. And they're going to have their IT team, or like whoever handles production is going to they're going to need control over the container and some of these pieces of it. And the data scientist and the machine learning engineer are going to need control over the machine learning pieces of it. So basically we had to re-architect this to basically allow a data scientist to take a whole bunch of files or like what their model really needs, and a handler, and specify that as a model, and then someone else to be able to specify the container and bring up node groups and different instance types, and then actually handle the deployment. And one final piece is that, and I think where sort of a lot of the value in machine learning is just going to get unlocked if we get this right or somebody else does, is once your model's in production, you're going to get from Spell or from a lot of different platforms, you're going to see a chart of latency. You're going to see how many requests succeeded. You're going to see, you might see it auto scaling. So you're going to get a whole bunch of stuff. You're going to know that it's working from an infrastructure standpoint. But how do you know that it's working from a machine learning standpoint? How do you know that it's not like producing all zeros and like everyone is seeing, the same pair of socks on the suggested products list or something like that? There isn't a great way to automatically do this. And the people that are responsible for operating it as an infrastructure project that are looking at it every day, those are the people who need to answer the question, is it working from a machine learning standpoint? So that's something that we've been working on for a while, is how can we take what we've watched, we can take the metrics, we can take this lineage that we have, because we know that model was trained on this job and that was this commit hash and that had these metrics chats. And that's all now serving in this infrastructure and producing these metrics. How can we take all of that and automatically give you some idea of like, well, the input distribution in training was this, but it actually looks pretty different. Maybe you should take a look at this. Maybe you should ping this person because they were the data scientists that trained it in the first place, that type of thing. And that's not out yet. Our model serving infrastructure is going to be launched imminently. So we'll follow up with Hussein and maybe send out a little bit of our materials about that. But just a lot of work to do there. Yeah, it's a huge, I could give another, and probably somebody else here from my team would be better equipped, but we could do a whole talk on model serving in production.
Yeah, really. Thanks for walking the dog on that.
Yeah, long-winded, but it deserved it, so.